Okay, we want to move on by considering one consequence of uniform continuity on an interval of real numbers. Well, let delta be such that we'll say f of x2 minus f of x1 less than epsilon for any x1 and x2, any pair x1 and x2 within your interval, which I'll call D. Okay, so the magnitude of f of x2 minus f of x1, the values of the function, less than epsilon for any x1, x2 in your interval, in your domain, provided magnitude of x2 minus x1 is less than delta. Okay, implicitly, D is a closed interval with a real line. Okay, well, then what we can say is, if this is one endpoint and this is the other endpoint, for any x, let's let this be an x, there's an interval, and I'm indicating the interval by a circle. I could indicate it just by an open set. But it's the interval on the line where magnitude of, well, x2 minus x1, and I'm just, haven't thought through notation. Okay, if this is x, then this interval, and let me go ahead and just indicate it by the standard open interval. I'm thinking more generally to higher dimensions and open balls, so I drew a circle. Okay, here's x. And here's the interval defined by, again, I need a notation. Okay, let's just let this be x1. Okay, so then this is the interval x1 minus delta, x1 plus delta. Okay, so there's a point in an interval. Now, we can take another point here and let this point be x1 plus delta. Okay, well, then you have an open interval around x1 plus delta. And I really guess I better draw this a little bigger, so let's do it again. Okay, so let's just say here's x1. And here's x1 minus delta, here's x1 plus delta. So here's an interval around x1 within which, for any point within this interval, the function value at that point differs from the function value at x1 by less than epsilon. Okay, Now I want to draw another interval. I want to draw the interval around the point x1 plus delta. Of course, that interval comes over right up to, just bumps right up against x1, but doesn't include it here. And of course, for any value of x within this interval, its value, the value of the function at that point differs from the value at x1 plus delta by less than epsilon. Okay. I can continue doing this. So I just have a sequence of intervals of length 2 delta that go as far as I want. And similarly, on the left, I have a sequence of intervals here. And so on. Okay, well, eventually, we're going to get to the end of the interval. And I'd actually kind of want to start this process at the end of the interval. Well, at the end of the interval, whatever the end of the interval is, if this is x equals b, and the other end is x equals a, then I can say, well, for any value of the function within a delta interval around b, but the delta interval only goes this far, because you don't even know if the function's defined on the other side of this point here, the other side of this endpoint. Okay? So if I continue the construction process here, I can have an interval here. And then another interval here. And eventually I'm going to overlap an interval I've already done. Or if I choose to now start at one end of my open or closed interval, I can do an interval here. I can do another closed interval here, another closed interval here, and so forth, until I end up with a closed interval that overlaps and that's a closed interval. I'll end up with an open interval. So I get open intervals all along here, until I end up with an open interval that overlaps the open interval around B. Now this can be written out in my intervals. You know, here's the first interval, here's the second, and then the third interval overlaps the second, and the fourth interval overlaps the third, and so forth. So I've got this, and so forth. Okay. A bunch of overlapping intervals that cover the interval D. Okay, so I'm going to claim that we can construct a series of overlapping delta intervals that cover closed interval D. So, consequence of uniform continuity. Okay, well, and this can be done for any epsilon. I can find a delta, so I can construct a series of delta intervals. So, again, this is a consequence of uniform continuity. What I want to do now is turn this around and say, okay, so if f is continuous on D, this is how we can do this. That is, construct a series of overlapping delta intervals to cover the closed interval D. Okay? To attempt a proof, we're going to say is it possible to satisfy continuity, the condition of continuity, but not to be able to do so? Okay, because if it's not possible, I mean, if it is possible to satisfy the condition of continuity but not be able to do this, then we can't say that continuity implies uniform continuity. Okay, well, we'll take up that idea in the next segment here.